Hey everyone, thanks for coming to our review session. I just wanted to start this off by saying that we're all really saddened about the news with regards to like Brad. He was one of our pilot leaders, and it's just like terrible that this happened. And our thoughts are really with like his family right now and his friends and those who knew him really closely. So we just want to thank you guys for being so flexible with us, and we're sorry about postponing the review session. But we just wanted to start this off by a moment of silence just to like think about Brad. So. Thank you guys for like participating in that with us. So this review session is going to be run like our other ones. We'll have Juan walking through our problem set, and then me and Molly will be monitoring the chats. So if you have any questions, feel free to ask either Molly or me. You can DM us or whatever, and we'll do our best to help out.
Great. Thank you, Sam. So yeah, before we begin, I'm just going to quickly plug in my iPad. But if you guys, in case you guys worked on the problem set, you guys know that this is a rather long set. So I will need to kind of, I will need to go a little quickly. So I won't stop after every single question for questions, but I'll stop like after every few, and then I'll take up questions for that last bunch that I had just done. And of course, if you have any questions while I'm working, you can feel free to ask any of the pilot leaders that are here in the chat. All right, so I'm going to start off, of course, with the first bunch, which involves the exam one material. So we're going to go and look at the hybridization of pretty much every atom that is not hydrogen. So you see here that first we have 4 carbon atoms, which I'll label here in blue. Okay, and what's notable about these 4 carbon atoms is the fact that they cannot resonate, right? They don't have any pi characters, any pi character, no pi bonds or lone pairs that are conjugated associated with them. So you see that because all the bonds that you have are permanent, then the hybridization for each will be sp3. Again, if we had any pi character associated with any of these, then it might change to sp2. Now for the oxygen over here in the middle, which I'll label in red. Now, while you do have 2 lone pairs on oxygen, remember that the lone pairs are only, or the lone pairs will be hybridized unless they can conjugate with some other, with some other double bond that's present in the system. And you see that, of course, there are no double bonds, and all the other atoms surrounding are sp3. So because of that, that oxygen there is sp3 hybridized. For the next one, so again, I will start off by labeling the carbons in blue. So we have 2 carbons here. And we see that the carbon on the left, again, it's just going to be a CH2 that's bound to a nitrogen and another carbon, all permanent, right? None of those is going to have, there's no pi character associated with that. So because of that, we could say that it's still sp3. And then for the other carbon, you see that you're going to have a permanent bond to carbon over here, a permanent bond to nitrogen over here, and you're going to have this bond to oxygen. Okay, so you see that this pi bond can technically delocalize, right? So that means that you don't hybridize that pi bond. In fact, you will never hybridize a pi bond. So because of that, you can go in and send your electrons up to oxygen, and then you'll get a carbocation here as a possible resonance structure, meaning that the carbon there is sp2. For the oxygen of the carbonyl, same idea. It has two lone pairs and a sigma bond that's permanently bound, but the pi bond, the electrons, they can technically be like delocalized just among those two atoms, not an actual like conjugated system, or I mean, like in this case it is, but that extra lone pair that it gets in the resonance structure, that's not permanent. So because of that, that'll also be sp2. And then lastly, the two nitrogens that you have there. So I'll start off with this nitrogen over here. I'll label it in green. So the nitrogen has a lone pair associated with it. Okay, I'll put the two lone pairs for oxygen here. But the nitrogen with that lone pair, you see that it has two hydrogens, a bond to carbon, and that lone pair. Again, that lone pair is not going to be next to any pi bond that it can potentially resonate with. Okay, you know that this pi bond is actually too far away, and you're separated by this sp3 hybridized atom. So it's going to be sp3. Now for the nitrogen over here, well, now you see that this lone pair, you can actually delocalize it into, you could delocalize it into that carbonyl. Okay, so you can go in and take those electrons, push them here, and then send those electrons up. What that tells me is that those electrons from nitrogen are not localized. Okay, if I were to draw the other resonance structure, you would see that it is delocalized. So because of that, that would also be that would now be sp2 hybridized. Okay, note here that we have sp2, sp2, and sp2, these three right next to each other. Okay, that means that this right here is an allylic pi system, which means a 3-atom pi system. Okay, so for our last molecule, you see that oxygen has two lone pairs, again, associated with it. Okay, so you have those two lone pairs. There's no pi bonds nearby. Okay, and then in addition, you're going to have a carbon that you're going to be permanently bound to, and a hydrogen. So because they're all permanent and you don't get to delocalize anything, it's going to be sp2. Okay. Then for the next few, so the carbons over here, I'll just do both of these guys at the same time. Again, they're CH3s permanently bound to something else. Okay. Chances are, most of the time, not all the time, if you see an sp3, if you see a CH3, then it's going to be sp3. CH3s don't have anything that can delocalize. So sp3 and sp3. In fact, that applies here with these CH3s as well. If you were to have any pi character associated with it, then it would have to be at least a CH2. Okay. And then this carbon right here, again, you have 4 sigma bonds bound to that carbon, no pi bonds on it, no lone pairs, no cations on it. It's going to be sp3. This carbon right here will be sp3 as well, because it's permanently bound to two of these methyl groups, an extra carbon above, and you have a hydrogen that's implicit. All right, now onto these two carbons. Now for those two carbons there in the middle, you see that, you want to note two things. One, they're attached to a triple bond, right? So that's telling you that those two pi bonds are not going to be hybridized. Second, it's linear. If you see that it's drawn out linear like that, that's going to be a dead giveaway that it's going to be sp hybridized. And then this should also serve as a reminder to you guys that for any atom that's sp hybridized, you should always draw it linear, don't draw it bent. Cool. So those are the hybridizations for those. Again, I'm going to keep going.
I think the OH group should be sp3.
Oh, my bad. Yeah, should be sp3. Thanks, Sam. Yeah. So Cool. Unless there's anything else that's like wrong or anything, I'm gonna keep going, and then maybe after like this page or something, I'll stop for questions. All right, I'll try and like leave this here so it's not like out of the way. Okay, number 2. So it says for the following molecules indicate the HOMO and the LUMO. Okay, so for the first one, so you could sit here and try and draw out every single pi molecular orbital, but that'll take you forever, especially for these rather complicated-ish molecules. But the whole point of this is that for your HOMO, you can see that you have these. So for your HOMO, you're going to have these pi electrons, right? If you were to go and then attack something, then it would be this pi bond that would go ahead and then attack. Okay, so that means that whatever you attack, your electrons will originate from your pi orbital. Okay, and then likewise, your LUMO, your LUMO should be anti-bonding, ideally here, unless it's an empty orbital, which is not. Well, I mean, between a sigma bond and a pi bond, the pi bond will be easier to break in this case. So because of that, it'll be pi star. Cool. For the next one, you're going to see that you have, so in this case, you see that you have, pretty much all sigma bonds here, no pi bonds, but you do have the lone pairs here on oxygen. Okay. Now, if you see the lone pairs on oxygen, then that should be a pretty big giveaway that your HOMO is going to be the non-bonding orbital on oxygen. Okay, and then your LUMO will actually be, in this case, the bond, once again, that's easiest to break. We don't have any bonds that are easiest to, or we don't have any pi bonds here, which would be easier to break, but we do have a sigma bond, and particularly this oxygen right here is very acidic. Okay, if you were to go and then deprotonate it, you would get O-, which is a very good conjugate base. So that means that your LUMO would be sigma star. All right, for the next one, so this next one, not gonna lie, is a little up to debate because the actual MO diagram says something different compared to like what one might expect. Okay, so I would just say, like, for this one, you probably won't get something as ambiguous as this, but for the purposes of learning, you're going to like see exactly like why we could make a case for either one. So for oxygen, so we can make the potential case that oxygen will get protonated first. Okay, because if you go and then protonate it, you don't lose the conjugated pi system. Okay, it is still conjugated. Now, looking at the lone pair on nitrogen, if you protonate the nitrogen, okay, then what you end up seeing is that the more electronegative atom is protonated. So, but you do lose your conjugated system here. All right, so we say that the HOMO is going to be non-bonding. So it's going to be non-bonding in either case. The actual MO diagram for this shows that it's going to be the non-bonding on the nitrogen. Okay. So again, you won't get something as ambiguous as this. So the technically correct answer is the non-bonding on nitrogen, but also you can make a fair case that it will be on the oxygen as well. So I'll just write or O for now. And then for your LUMO, you're going to see that once again, you have a pi bond. If you have a pi bond, you can make a pretty safe bet that unless there's like a carbocation or a boron or something, that's going to be the bond that will be most easily broken. So your LUMO here would be pi star. All right. And then for our, let me move this up, or let me move this out of the way. then for our last one, well, this one is or besides the ring, it's completely saturated. Okay. So you don't have any lone pairs, you don't have any pi bonds, no cations, no borons or anything, just a complete hydrocarbon that's saturated besides the ring. Okay, so because you only have sigma bonds here, that means that your HOMO has to be sigma, and then your LUMO has to be sigma star. All right, cool. So that's your pi. So that's your HOMO and your LUMO for each of these molecules. Cool. All right, number 3 is finding the number of primary, secondary, and tertiary carbons. This is not really too hard of a problem, but it can be rather tricky, especially if you're not keeping track of your carbons. Okay, something that is very, very useful and provided to us here is the molecular formula. Please take advantage of your molecular formula. Okay, that tells you how many carbons you have. So the number of primary, secondary, and tertiaries. I'll actually also add in quaternaries as well. Should add up to 21. Okay, so I'm gonna go and I'm gonna color code because I can. I'm gonna start off by trying to find my primaries. Okay, for this it's pretty easy to miss. So if I happen to look like I'm missing one, just like let me know. But right off the bat, I see that there is one right over here. Okay, moving along, we see that there is one over here, and there is one over here. Remember that primary means that it's only bound to one carbon, not that it just has one bond. Okay, I think that's it. I don't think I'm missing anything. So if that's the case, for primary, we just have 3. For secondary, so it seems like there's actually quite a bit of secondaries here. So be extra careful when you're going and finding this. So let's see, start off over here. We see that this guy looks like it's going to be secondary because of the fact that it's only bound to 2 carbons. This one, it has a double bond, but don't worry about the double bonds. Okay, it's still only bound to 2 carbons. This is bound to 2 carbons. This is bound to 2 carbons. Okay, moving along, we have this one bound to 2 carbons. This one, this one, this one. All right. I don't think I'm missing any. Cool. So if that's the case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we've already accounted for 14 of our carbons. We still need 7 more. All right. Now, tertiaries, you want to go and then see what's bound to 3 carbons. Okay, so be mindful of like the ones that have hydrogen in there. Remember that there's still that tertiaries will often still have hydrogens. Okay, except for this one, because it's an sp2 hybridized one, so it's missing a hydrogen, but it's still only bound to 3 carbons. Okay, we have one over here, one over here, one over here, and one over here. Cool. 1, 2, 3, 4, 5. All right, so if I did my math right, there should be only 2 tertiary, there should only be 2 quaternary carbons, because right now I've accounted for 19. Okay, and then that means that this guy over here and this guy should be the last 2 that I'm accounting for. There should be 2, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21. Cool. So that's 21 carbons accounted for. That means that we have successfully found every single type of hydrogen or carbon that we have.
One quick note, Juan, for your little pink drawing in the upper left, you say plus on the more electronegative atom. It should be the less electronegative atom.
It should be on the
right here. That should be the less electronegative atom.
Sorry, yeah. I am. Cool, thank you. All right, yeah, so we have this. Then number 4. So it says to draw the pi molecular orbitals for the following system and then indicate the HOMO and the LUMO. All right. So here we see that we have a 5-atom pi system. Okay. 5 atoms, because I know that every single atom here is sp2. Or every non-hydrogen atom, of course. So remember that we have like a little rule that says that so that your number of atoms in your pi systems is going to equal to the number of your atomic orbitals. That's going to equal to the number of your molecular orbitals. All right, so now let's go and put everything together. Now, you see here that we have, so I'm going to go ahead and draw one of my molecular orbitals. Again, that has to consist of my of the same, or 5 atomic orbitals, and I'm going to get 5 of those. I'm going to cut into the problem because I can. Okay, so like this. Remember that for all of these, we're going up in energy. All right, and okay, and then we can label these pi 1, pi 2, pi 3, pi 4, and pi 5. All right, so remember that for our lowest energy level, for pi 1, we're going to start off having 0 nodes. The way we have 0 nodes is that each of these is going to face the same direction. Okay, then pi 2. So now we're going to get into something a bit interesting here, because remember, we want to try and like have this model a nice simple wave function, or a nice simple symmetrical wave function. But the only way I can get it being symmetrical is if I cancel out one of my atomic orbitals here. So I'm going to have to do just that. Boom, 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 boom. For pi 3, I'm going to have this. So now I have 2 nodes. Again, the only way that I can make it nice and symmetrical is by canceling those 2 out like that. For my next one, I'm going to have, so the best way that I could do this, it's going to look a little weird. So we're going to have this, then like this. And then the last one, for any pi molecular orbital, your highest energy level will just be alternating. So it'll be up, down, up, down, up. Doesn't matter if you start off with up or start off with down, as long as you're consistent. Okay, but just to sum up, you see that we have no nodes in our first one, have 1 node in our second one, 2 nodes here, 3 nodes here, and 4 nodes here. All right, so yeah, now let's go ahead and find out our HOMO and our LUMO. Okay, before I do that, I'm going to quickly remind you guys that there is a non-bonding line. Remember that non-bonding line is going to go right across the middle of the system. Okay, if there's an even number of atoms in the pi system, then it won't intersect any orbital. But since there's an odd number, it's actually going to go and intersect pi 3. So that's, again, your non-bonding orbital, and that tells you that there is a non-bonding orbital for this, which makes sense because you have a lone pair in the pi system. So pi 3 is going to be non-bonding. Pi 4 is going to be anti-bonding, and pi 5 is going to be anti-bonding as well. All right, so now to go and then find my HOMO and my LUMO, I need to go and then calculate, I need to go find the number of pi electrons I have in my system. Well, I have 2 pi electrons here, 2 pi electrons here, and 2 pi electrons here. Okay, the lone pair counts as pi electrons because I can actually go and then delocalize it into my system, as you see here. Okay, again, it's all sp2 atoms right next to each other. All right, so that gives us a total of 6 pi electrons. All right, and then if I go and then I'll do it, I guess, over here. So if I fill up my orbitals, all right, then you see for those 6 pi electrons, I'm going to do 1, 2, 3, 4, 5, 6. Okay, so that means that my HOMO is going to be pi 3, and my LUMO is going to be pi 4, but you should denote that it's antibonding. Cool. All right, so this is the end of the first page. So I will very quickly stop for questions because I have long ways to go.
Could you please explain the non-bonding on nitrogen again instead of on oxygen for question 2?
So the actual pi, like if you actually look at the orbital itself, like the MO diagram actually says that the HOMO would be the non-bonding on nitrogen. Okay, I don't know if it was like on any pilot set or like on any back test this semester, but if you look at it like that is going to be the HOMO. However, the case that I would personally make, and the case that would probably be a little more intuitive, is to put it on oxygen because it leaves you with a more conjugated system. Any other questions? All right, I'm gonna go ahead and move on to the next page. So I'm gonna consider ammonia. Okay, so the ammonia molecule looks like this. I'm gonna be extra and draw it as a tetrahedral because I can, but that's also how it actually is. Here, let me actually move this guy down here. Okay, and then it's telling you that the hydrogens on ammonia are sp 3.5. Okay, so well, the hydrogens themselves are, it's actually the NH bonds. So sp 3.5. Then it doesn't give you the hybridization of the lone pair, so we actually have to go ahead and then calculate it. All right, so remember that, I mean, before you like do this problem, I guess it's good to remind you of the hybridization index. So you have something that's SPN hybridized. That means that you're going to be 1 over n plus 1 S character and n over n plus 1 P character. Okay, so now we're going to go and calculate everything. So NH is sp 3.5, which means it's going to be 1 over 4.5 S and 3.5 over 4.5 P. Okay, and lone pair, we don't know what that's going to be. So what I want to start off by finding out is how much character I have already used for all of these, or rather how much S I have remaining. And that's calculated by doing 1 minus S used. So the S character that you've used is going to be 1 over 4.5 times 3. Okay, because you have 3 NH bonds. So that'll be 1 minus 3 over 4.5, or 1 minus 2/3. Okay. Once you go and then subtract 1 minus 2/3, you get that you have 1/3 left. So that's going to be 1/3 S character for that lone pair. That means that you have 2/3 S character. Sorry, 2/3 P character, right? Because you know that ultimately your S and your P character both have to add up to 1. So if I have this and this, that means that the hybridization of the used for the lone pair is going to be it's going to be sp2 hybridized. Cool. All right. For the next one, so it says to indicate the most acidic molecule, and then from each of those molecules, highlight the most acidic proton. Okay, so here in this case, we want to go and find out which part of the molecule is going to be the most acidic, which it's going to be either the amine or the alcohol. And if you try drawing out the conjugate bases, Well, you see that oxygen is going to have a negative charge. Oxygen is actually going to be much happier with that negative charge than nitrogen is. So that means that that the molecule on the right is going to be the most acidic, with of course the most acidic proton being the one on the alcohol. Okay, next up, we're going to have acetic acid versus fluoroacetic acid. Okay, the one thing that we know about fluorine is that fluorine is very electronegative, so it induces some sort of a dipole. So we have a partial negative here and a partial positive here. So when we go and then work with that, if I were to go and then draw my conjugate base, partial negative, partial positive. Now this negative charge on oxygen actually, serves a purpose now, okay? And that's to go in and stabilize that partial positive that you have there. That's really good. You don't have a partial positive, you don't have a partial positive like that to stabilize for your other acetic acid. Okay, it's just a negative charge, just like kind of chilling there with the carbonyl. Okay, so because of that, by induction, so we know that this proton will be the most acidic, but this compound overall will be most acidic. Okay, let me just write the trends real quick. For this one, it's electronegativity, and then for the bottom one, it's going to be by induction. And remember that there's two subsets of induction. There's either the presence of an inductive group or the proximity. In this case, it's just the presence. All right. For the next one, so you see that you're, once again, going to have this acidic proton over here on the alcohol. Now, if I go and then deprotonate, we are once again dealing with the same case that we had previously. But in this case, your inductive electron withdrawing group is going to be the carbonyl. So you have a partial positive on this carbon, partial negative on this oxygen, partial positive, partial negative. And again, that oxyanion is stabilizing that partial positive. Oxyanion is stabilizing the partial positive here. However, what we end up seeing is that this partial positive is a lot closer to this negative charge than this one is to this one. Okay, and remember, opposites attract. So because of that, the one that has the closer inductively withdrawing group is going to be the one that is most acidic. Okay, so this is going to be induction by proximity. All right, next one. So we see that we have acetylene and we have ethane here. We see that for acetylene, of course, these guys, so the carbons are going to be sp hybridized. And then these CH3s are going to be sp3 hybridized. All right, so because we have sp versus sp3, you know that greater S character is going to be more electronegative than lower S character. And we can tell that sp has greater S character. Okay, so because of this, by hybridization, rather electronegativity and hybridization, the acetylene's proton ends up being more acidic. All right, lastly, for this one right here, what you end up seeing is that you have the proton here that's acidic right in the middle, and you have this other acidic proton right here, okay? Now, note that you might think that the protons on the aldehyde are going to be acidic because of the fact that they're on sp2 hybridized atoms, okay? While that's a valid argument to make, what we actually end up seeing is that if I were to go and then deprotonate in the down the middle over here, I get a negative charge. What stabilizes this even more is that I deprotonate an sp3 atom and now it becomes sp2. Okay, and that actually makes it much more favorable. In fact, the big thing that this proton has going for it, same with this proton over here, is that it is now part of a conjugated system. Okay, meaning that I can take these electrons and I can either delocalize it in this direction or this direction, or I can delocalize these electrons into this carbonyl. Okay, so because of this, we could say that this guy on the left, with this being the most acidic proton, is going to be most stabilized, and in this case, the stabilizing factor is going to be resonance, particularly because of the length of the pi system. Okay, because here you see that we're making this into a 5-atom pi system, whereas over here we're making this into a 3-atom pi system. Okay, so again, make sure that you guys are used to your trends in acidity and basicity, and you're able to reason why something might be acidic or basic, right? Again, I mentioned this at the beginning of the review session on Saturday, but understanding acid-base chemistry will help you really good with the new material. So definitely take some time looking at this if you're still not sure. All right. Lastly, so it says to complete the following acid-base reaction and indicate the HOMO and the LUMO. Cool. So particularly there are some molecules that will always be LUMOs and some molecules that will always be HOMOs. Okay. In the case of boron right here, boron has a very characteristic empty p orbital. Okay, so you have that empty p orbital on your boron. That's going to be your LUMO. Okay, your lowest unoccupied molecular orbital, where you're going to be sending your electrons to. And then likewise, over here, we know that acetate is a good nucleophile. So in this case, it would just be the non-bonding electrons on oxygen, which will serve to be your HOMO. Now, the next thing is, of course, going and then drawing your electrons towards your boron, your empty p orbital, and that's going to go and then give you a structure that looks like this. But surprise, this structure will not get me full points on an exam. I'm missing something. What am I missing?
The positive charge on boron.
Positive?
Negative, my bad.
Negative, right? Yeah, just remember I have like a little trick that the overall charges on your starting materials will be the same as your overall charge in your product. Okay, so if you have an overall negative here in your reagents, then you should have a negative somewhere in here. All right, end of this page. Any quick questions before I move on to constitutional isomers?
Quick question, Juan.
Mm-hmm.
Oh no, never mind.
Okay, cool.
Or actually, wait, okay, I remembered. For number 5,
Yeah.
can you always say that there will be, I guess, like 1 S and then by extension 3 P's?
What do you mean?
Like when you're talking about S left equals 1 minus S used, right?
Mm-hmm.
So like if you wanted to calculate with P first, would you do 3 minus P used, or like?
Yeah, if you were to calculate with P, you would start off with 3. So it would be 3 minus whatever P character you use.
Yeah. Okay.
Cool. Okay, next up. So everyone's absolute favorite thing ever, constitutional isomers. So it says, draw all the constitutional isomers of C8H16 that contain a cyclopentane ring. Okay, cyclopentane, you guys should remember, is a 5-membered ring. So that means that we have 3 carbons left to play around with. So what I personally like to do is that I like to start off with my straight chain right here. So this is, the straight chain of C8H16. And what I like to do is that I like to take that N-methyl group and kind of just go and then like move it around in as many places as I possibly can. So here's one. Here's another one, right? I just moved this guy over here. I'm going to go and then move this methyl group over here now. Okay, you don't have to do it in this order, obviously. I'm showing you guys my thought process. And then I'm going to keep moving around this methyl group around the ring until I have to stop. One here. And one here. Okay, I'm not going to continue because if I go and I try drawing a methyl group over here, then it's going to be the same as the structure that I have here. Or like the same structure that I have drawn here. All right, now I'm going to go and then take this methyl group and I'm going to keep moving it around the ring. Okay, and then I am going to go and then move this over here. All right, and then besides this, I think the other one that I'm missing is this. All right. I believe that is everything for this. I don't think I'm missing anything. Can you guys think of one that I'm missing by any chance? Oh, yes, I can. This one. Right here. Yeah, I think that should hopefully be everything. So now I want to go ahead and take this and find out how many possible stereoisomers I'm going to have. Okay, so I'll start off with my top one, my top left. So I don't have any chiral centers here, right? So I could say 2 to the 0 for no chiral centers. That's going to be 1. This one, no chiral centers, right? This is just only substitute on the ring, symmetrical on either side. And this one has 2 methyl groups here. So again, 2 to the 0 equals 1. Next one, again, no chiral centers, 2 to the 0 equals 1. Next one, you actually have 2 chiral centers being over here and over here, okay? Not meso, so don't worry about that. So it'll be 2 to the 2 equals 4. Here you have 1, here you have another, 2 to the 2 equals 4. Here you only have 1 chiral center, right? Again, this other one is not a chiral center because you have 2 methyl groups here. So it'll be 2 to the 1 equals 2. For the next one, here, let me push this over here to the end. I have a reason for that. For this next one over here, you see that you once again only have 1 chiral center. So that'll be 2 to the 1 equals 2. And then for these two, okay? So for these two, you see that you have 2 chiral centers in each. But you do also have a plane of symmetry, that being right over here. Now, this plane of symmetry makes things a little tricky, right? Because notice that you have this methyl group that is on your plane of symmetry. So if that methyl group is on your plane of symmetry, then you're going to have a meso compound with pseudo stereocenters. Okay, right? That pseudo stereocenter being that substituent that is on that plane of symmetry. Okay, meaning that it can be what you could, that means that it'll give you 2 meso possibilities for these. Okay, so remember that for pseudo stereocenters, the way that I would do it is that, I would do 2 to the n, then I would do -1 for the fact that it's meso, but then I would actually add 1 back in because you have 2 different meso possibilities. Okay, as opposed to just 1. Okay, if you had a meso possibility, then you would subtract 1 and just leave it at that. So of course, these guys will cancel out. Okay, so in this case, all you really have to do is just 2 to the 2. Okay, so you're gonna have 4 for this, and then 2 squared equals 4. Now I go and then add up the number of stereoisomers I have. I'm going to end up with 1, 2, 3, 7, 11, 13, 15, 19, 23. So it looks like I have 23 stereoisomers. And because these 2 constitutional isomers are, they're symmetrical, and they're the ones that have your meso possibilities. But of these, 4 of these stereoisomers will be meso. And because you guys are all such wonderful Orgo students, I will draw out the 4 meso ones so you guys can see.
Why only 4, not 8?
Where would you get 8 from?
I thought 4 pseudo meso each.
Are all 4 of them meso?
Oh, no. Okay.
Well, so those would be the 4 meso compounds you get. Okay. Again, that pseudo stereocenter is there to make your life slightly more complicated. Cool. So constitutional isomer problems, some of them will be easier to organize than the others. This one, because it's all carbons, it's one of those types that's a little harder to organize. So make sure that you guys are just trying to, come up with like a way where you can go and then check your work to make sure that you're not missing anything. Cool. It is now chair o'clock, so we are going to go and look at the difference between the 2 chair conformations for the following molecule. Okay. You guys know that I personally like numbering these things to make sure that I'm translating it properly into the chair. So if I number this 1, 2, 3, 4, 5, 6. Remember that my little rule is that if it's dashed, it's going to point down in the chair. And if it's wedged, it's going to point up in the chair. Okay, so I'm going to number this 1, 2, 3, 4, 5, 6. And then you see that my carbon number 3, you see it's going to be wedged, so it's going to point up here. 4, it's going to be wedged, so it points up, but now it's going to be up equatorial. Remember, you can't have 2 up axials next to each other. And then 6, you see that it's going to be pointing down, so you're going to have this down axial over here. So that's 1 chair conformation. Now I want to go and draw the other one. Okay, so for number 3, you see that you're going to have, 3 was axial here, so now it's going to be equatorial here. 4 was equatorial, now it's going to be axial. 6 was axial, now it's going to be equatorial. Now you want to go and then find out how many 1, 3 diaxial and how many Gaussian interactions you're going to have. So you have 1, 2, 1, 3 diaxial interactions up here. You're going to have another 2, 1, 3 diaxial interactions here. And in addition to that, you're also going to have a Gaussian interaction here, right? Because they're both adjacent to each other and they're both pointing up, okay? So that means that you're going to have a total of 5 times 3.8. Let me do this color. 5 times 3.8, I'm not going to calculate it, whatever that is, that's going to be your energy for that chair. And then for the other one, well, you see here that we have, once again, 2 1-3 diaxials over here. So we have boom and boom. And in addition, you're also going to have a gauche. That gauche will be over here. Okay, 2 up and adjacent next to each other. So you go and then do the calculation for that. It would be 3 times 3.8. Again, these values will all just come from your table in the back. Now you do some math. So that means that 5 times 3.8 minus 3 times 3.8. That'll give you 2 times 3.8. Okay, and that means that your energy difference will just be 7.6 kilojoules per mole. Cool. And then, so I'll leave that up. I guess since I have to scroll all the way down for the next one, I'll stop here for questions.
One just quick question again, sorry.
Mm-hmm.
If hydrogen or methyl is equatorial down, does that mean it gets switched to axial up, like when the chair flips?
If it's equatorial down, then it will become axial down in the next one.
Axial down?
Yeah.
Okay.
Sorry, could you just re-explain why it's the 4 meso compounds and not 8?
Well, remember that if you draw out all the stereoisomers for this, then you're also accounting for the stereoisomers like this one. Right, and you know that this one's not meso. Okay, so, and then this one, also this one. Okay, so like these guys are not meso. Okay, and then the same applies for like the other one as well. So of those 4 stereoisomers that you get, only 2 of them will be meso, not all 4. That makes sense?
Yeah, thank you.
Mm-hmm. Okay, I'm gonna go down to the MO problem now. So it says some of the important MOs for acetaldehyde right here are shown below. The lowest 6 MOs are omitted. Okay, I think this for an exam question, this would be very useful to highlight. So that way you're not accounting for those. Identify each of the drawn orbitals and indicate the HOMO and the LUMO. Okay, so remember, in order to do this, what I personally like to do, I keep saying remember, I don't know why, but I like to go and then draw out pretty much all the atoms here without any bonds yet. All right, so first I want to go in and identify how many sigma bonds I have, and you see that I'm going to have a total of 1, 2, 3, 4, 5 sigma bonds. So if I have 5 sigma bonds, and I'm also going to have 5 sigma stars. Okay, next one. So I'm going to have.
You dropped a hydrogen on your methyl group.
I did, yep. Thank you. So it's 6. Okay, then sigma, I'm sorry, for pi, we're only going to have 1. And then for non-bonding, you're going to have 2. Okay, so now let's go ahead and, see like how the order for this is going to look. Now, the ones that you can be certain about, or the only things you can be certain about are the sigma ones, right? Because pi star, non-bonding, they can be kind of like just sprinkled in there and kind of confusing. So you know that your lowest ones will be your 6 sigmas. And your highest ones will be your 6 sigma stars. Cool. So that means that your lowest 6 MOs are omitted. That means that we're not taking into account those 6 Yeah, we're not taking into account those 6 sigmas. Okay. So now let's go and see, and then somewhere in here, we're going to have our pi's and our non-bonding. Okay. So not necessarily in that order. Okay, so now in order to go in and identify which ones are going to be your pi's, so remember that these MOs are largely modeled off of your pi MO diagrams. So remember for this one, your 2 pi MOs would look like this, since it's a 2-atom pi system, right? And then you know that you would have, you know, some sort of like MO that looks like this, and then the second one looks like the one up here, right? So this would be your pi 1, and then this would be your pi 2. Well, the ones that look like your pi 1 and pi 2 are this one here and this one here. Okay, so those, and then in this case, you see that there is no non-bonding orbital here because of the fact that your non-bonding line would just be right down the middle of your system. So there is no non-bonding corresponding to your pi system. However, there are 2 non-bondings like this that we have to account for here. And the way that you know that these orbitals are non-bonding are by the fact that their shapes show that you have a large amount of electron density about the atom that has your lone pairs. Okay, so these 2 would be non-bonding. Do note that these non-bondings are not in your pi system, which is why they don't show up in your pi system MO. Cool. So I've gone ahead and identified those orbitals. You don't have to. Oh yeah, and also like in terms of what pi 1 and pi 2 is, remember that anything above. Sorry, let me plug in my laptop now. Anything above the non-bonding line here will be anti-bonding. So pi 2 is pi star. So that means that this guy up here is going to be pi star. All right. So yeah, now you want to go and then find your HOMO and LUMO. Now, because here we have a full molecule molecular orbital diagram, it's actually different from how we calculated the other HOMO and LUMO. Oop. I don't know what happened there. Okay, and what you want to do is to count the number of valence electrons on each atom. So hydrogen has 1, 1, 1, and then 1 over here. Carbon has 4, and then oxygen has 6. So you want to go and then add all those up, where you get a total of 6 plus 4 plus 4. That is, that's 14, 15, 16, 17, 18. 18 pi electrons. Okay. So now you want to use those 18 pi electrons to go and then fill up those orbitals. Okay, remember that of those 18 pi electrons, 12 of those were in your bottom 6 sigmas. Okay, so if you want, I'll draw 6 sigmas. Ugly, but whatever. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those 12 were omitted from this drawing. Then we have 13, 14, 15, 16, 17, 18. Okay, so that means that from this, your HOMO is going to be your non-bonding, and then your LUMO is going to be your pi star. Okay. Oh, sorry. For some reason, it got frozen. All right, cool. Any questions about this before we go on to StereoChem? Okay, so now StereoChem. Now, StereoChem can either be not too hard or can be really hard, depending on if you have to go and then convert between different projections, like that very last problem that you see down there. So I'm going to go and then just like solve through these by, of course, finding your absolute configuration for each chiral sensor. For the first one, so you see that you have a chiral center here and a chiral center here. Your absolute configurations are going to be 1, 2, 3. This is going to be S. And then for this one, you're going to have 1, 2, 3. This one's also going to be S. Okay, remember that in both cases, I actually had to go and then flip the absolute configuration because of the fact that my lowest priority was pointing forward. Okay, so that's just something to take note of for that. So I have S versus S. They're the same compound. Same compound. Same constitutional isomer, same absolute configuration. That means that they're going to be identical. Okay. For this next one, not gonna lie, I don't even have to find absolute configuration because I see one thing that jumps out at me, and that is this double bond right here. Notice that in one, my double bond is going to be Z. The other one, my double bond is going to be E. Okay, you can also say cis and trans. Right off the bat, you could tell they're not mirror images of each other. So because of that, they are going to be diastereomers. Okay. Next one. Not gonna lie, I don't even have to find absolute configuration for this because I noticed something. Okay. Notice where the bromine is in each one. Okay. Notice that the bromine is on a primary carbon in this one. And here, notice that the bromine is on a secondary carbon. Okay. So if you have bromine on a primary and bromine on a secondary in the other one, right off the bat, that tells you that they are not even the same constitutional isomer. Okay, so they have to be constitutional isomers here. See, identifying things like this will really help you save time on your exam, okay? Because then you're gonna find out absolute configuration and be like, oh wait, they're probably enantiomers or diastereomers, but then you realize that they are actually not even the same constitutional isomer to begin with. All right, next one, this one might actually help. It might actually help to go in and find your absolute configuration. You have one chiral center. And if you find absolute configuration, you get 1, 2, 3. That looks like it's going to be S, but you have to flip it, so it's going to be R. And then for this one, you're going to get 1, 2, 3. That looks like it's going to be R, but you have to flip it, so it has to be S. So R versus S, you only have one chiral center. They are going to be enantiomers. All right, next one, you see that I have total of 2 chiral centers here. So I want to go and then find out what my absolute configuration is for each. For this, it might actually really help you to number your carbons just to make sure that you're dealing with the same thing. So this will be 1, this will be 1, and then this will be 2. Okay, so for absolute configuration, you see that I'm going to have 1, 2, 3. Looks like it's going to be R, but remember that the hydrogen is going to be wedged, so it's actually going to be S. Then for the second one, we have 1, 2, 3. Looks like it's going to be S, but you actually have to go and then flip it, so it's going to be R. Again, what's making you having to flip is the fact that the hydrogen here is wedged. Now for the second one, 1, 2, 3. And that's going to be R. And then for the second one, you have 1, 2, 3. That is going to be, it looks like it's going to be S, but sorry, it looks like it's going to be R, but you actually have to flip it because your hydrogen, your implicit hydrogen is pointing forward. So it's actually going to be S. So here we have that carbon 1 versus carbon 2. Carbon 1 is going to be S in one of them, and then R in the other, and then 2 is going to be R and then S. Okay, so they are exact mirror images of each other. So that means that they're also going to be enantiomers. Okay. And we have two more, but these two, in my opinion, are the trickiest ones on this problem set. Okay, so for the one on the left, for this next one, I want you guys to like do something first. And if you have a model kit, this will help you out a lot. But never trust your lowest priority being planar. If your lowest priority is planar, then that will make your life significantly harder. Okay, because the wedge can either be on the left or the wedge can be on the right. Okay, so what you want to do is maybe draw like a little perspective drawing. Again, model kits help with this, where you're looking down the plane like that, and pretty much your leaving group will be in the back. So you're gonna have this little Y shape. Okay, with your hydrogen kind of just like being like in the back. I'm not gonna draw it out. But then if you look at it from that direction, okay, so you see, like, I'm gonna do this with my hands. If you want, you can do it with your hands too. But at least from my perspective, what I see, if I look at it from this direction, my chlorine, which was originally in the back, will now be on the left. Okay, my bromine, which was originally pointing forward towards me, will now be on the right. And then the rest of the molecule, the isopropyl group, will be, it'll be like that. Okay, so this is just pretty much a perspective drawing, looking down that, and I want to go and then find my priorities for this. So I'm going to have 1, 2, 3 for this. Then when I do that, again, knowing that my hydrogen is in the back, this is going to be S. My other one's a lot easier because my hydrogen is pointing forward, so I could just reverse it. So I'm going to have 1, 2, 3. That looks like it's going to be S, but I actually have to flip it. It's going to be R. Okay, so because of that, these are going to be enantiomers. All right, and then for the last one, don't try and find stereochem using a Newman projection. Okay, that tends to be really hard. What I personally would like to do is to go and pretty much, I'm actually going to redraw this Newman as a eclipse conformation. Okay, and particularly I want to make it eclipsed such that they're both kind of like Y-shaped, not Mercedes shaped. So this will come here, this will come here, and then this will come here. And then I end up seeing, when I draw it, so the back carbon that's Y-shaped will stay the same. Oop. So bromine, hydrogen, CH3. Okay, and then you're going to have CH3, hydrogen, and chlorine. Okay, now what I want to do is to translate this into a Fisher projection. Okay, and you can actually make this into a Fisher projection by just looking at it from above. Okay, what that means is that this H and the CH3 will actually end up being on your wedges. Okay, so this is my Newman projection, and I call this, if I call this carbon 1 and I call the back one carbon 2, 1 and 2. So I see on carbon 1, my hydrogen is pointing down. So that hydrogen will be dashed over here. Okay. And then likewise, my CH3 will be, will be dashed as well on carbon 2. Okay, and then from this perspective, you could see that your chlorine and your bromine are going to be on the left side. So I guess I'll highlight that in yellow. So chlorine is on carbon 1. And then bromine is on carbon 2. And then you're a methyl group. And your hydrogen will be like this. Cool. And now I have successfully converted my Newman into a Fisher. Okay. If you think about it, at the end of the day, all a Fisher really is just an eclipse Newman projection. So now let's go and then find our absolute configurations because it's really easy to find it with a Fisher projection. So I'll start off with this compound right here. So you see I have, let's see, first priority, second priority, third priority. We're going in this direction, but we have to flip it. So it's going to be R. And then for this one, we have 1, 2, 3. We're going in this direction, but we have to flip it. So it's also going to be R. Okay, so they're both R. And remember, if you'd like, we can go and then number. This will be carbon 1 and this will be carbon 2. So both carbons 1 and 2 are R. Then for the next one, we can see we have 1, 2, 3. So it looks like it's going to be R. And in fact, it is going to be R because of the fact that your hydrogen is pointing back. And then for your next one, you're going to have 1, 2, sorry. Wait, hold on. Sorry. For this one over here. Sorry, this should be 1, 2, 3. Yeah, still are. Never mind. Cool. Then for this one, it'll be 1. Yeah, sorry. 1. What are you doing? There we go. 1, 2, 3. It looks like it's going to be S, but you have to flip it because your hydrogen is forward, so it's going to be R. Okay, so with that, they're going to be identical molecules. Well, let me just double check this real quick. Yeah. Cool. So that's stereochem. Little tedious, but remember, if you can find a shortcut, then definitely go with that. Any questions on this? I think that's finally the end of exam 1.
So regardless if the first priority is wedged, if the hydrogen is wedged, you have to flip the stereochem.
Yep. Or like, I mean, if the hydrogen is wedged, then nothing else can be wedged. So as long as the hydrogen is pointing out in the front, then you would have to flip it. If it's in the plane, then you would have to do this little complicated thing that I did here.
Thank you.
Any other questions? Okay, exam 2, which is thankfully less tedious than exam 1 material. So it says to rank the following carbocations in terms of stability. So I'm going to go in and identify them first. You see that this is a tertiary allylic. Then this is going to be a secondary vinyl. Then this one is going to be a primary alkyl. It's alkyl because it can't resonate because you have this sp3 atom in the middle. And then here you're going to have a tertiary alkyl. Okay, so I can identify some contenders for least stable right off the bat. If I call this A, B, C, and D. Well, I could tell that vinyl carbocations are a huge no-go. Okay, we do not like vinyl carbocations. Reason why is because of that lack of hyperconjugation and also because of the fact that you have a positive charge on an sp atom, which is electronegative. Okay, slightly more stable than that, but really not by much, is going to be your primary alkyl. So that's going to be C. And then between A and D, they're both tertiary. The only difference is that one is allylic, the other one is alkyl. That means that A can resonate and D cannot. Okay, so remember, we prefer resonance over non-resonance. So A will be greater than D. And that is going to be your carbocation stability for this. Now for the next, we have some alkyne reactions. So this first one over here, that's NaNH3 at negative 78 degrees Celsius. That's your dissolving metal reduction. Okay, so remember, be sure to be consistent with your number of carbons, 1, 2, 3, 4, 5. Remember that your dissolving metal reduction will reduce into the transalkene. 1, 2, 3, 4, 5. So like that. So that will be your first one. And then likewise, H2 Lindlars does the same thing, except you go and then reduce into the cis alkene rather than the trans. Cool. Now for the next one, for NBS and water. So remember that this will kind of undergo the little bromonium ion intermediate first. Okay, and then remember that your water will eventually want to come in and then attack over here. And then in doing so, you're going to end up with a compound that looks like this, right? But remember, the big thing that you have is an enol. Okay, I know some of you are still a little shaky with identifying enols and tautomerizing, but yes, that will have to go and then tautomerize into the ketone. Don't ignore tautomerization. Okay. Next one, 9-BBN and THF. Remember that that will just go and then add it to your anti-Markovnikov position. So it'll add in over here. So you would end up with an enol that looks like this. Right, and then that will just eventually go in and tautomerize into, in this case, the aldehyde. Cool. And then those are going to be the products of all your alkyne reactions for this one. For number 3, it says to draw 2 possible starting materials for the following reaction. I'll zoom out at the end. Okay, but importantly, what you want to note first is that the molecular formula here is C10H12. You only have 5 carbons here. So if I have 5 carbons here and I have 10 in my starting material, what does that tell you about your product?
There's 2 of them.
Yep, you have 2 of them. So that means that you kind of like want to like play around and see what potential things you have for this. Let me draw it like this. Oh, nice. I'm getting a call from Spam Risk. Okay, so I have this. And I want to try and like draw both together so I can kind of like maybe deduce something that I can get from the 2 of these. All right, cool. So I have 1, 2, 3, 4, 5, and I'll call this 6, 7, 8, 9, 10. So maybe what I might want to do is to combine 2 and 7, combine 3 and 8, and combine 5 and 10. So if I combine 2 and 7, what I'm going to end up getting is this compound right here. Not particularly a compound I like, but I'll ask you guys why I don't like it in the next thing. And then I have 1, 2, 1, 2, 3, 1, 2, 3. Okay, so it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, my next question is why don't I really like this compound too much? It's valid, but why don't I like it?
4-membered ring.
4-membered ring, yes, but what's so bad about that particular 4-membered ring?
The angle strain.
Angle strain, but in terms of like
It's
property-
anti-aromatic.
Anti-aromatic, there you go. Cool. Yeah, so that's gonna be kind of, you know, unstable. Okay, maybe another possibility is if I have, and again, there are many possibilities. I'm just gonna draw out 2 here because of time, but as long as you have the right number of carbons and you check that it's correct, you're good to go. You see that you can go and then put these 2 together. So let me do the same numbering that I did earlier. 1, 2, 3, 4, 5. I can go and then put 2 and 5 together. Then I'll put the other equivalent, 7 and 10 together. And then I'll put 3 and 8 together. So you know that putting 5 and 2 together, so 2 and 5 together will make a 4-membered ring. Okay, here's 2, here's 5. 1, 2, 3, 4. You know that 4 has nothing on it, but then 3 is going to be double bound to the other compound. So this will be double bound to 8. All right, so you have that 3 double bound to 8, and then afterwards, you have 9, which has nothing, and then 10 and 7. So these two are bound together, and then 7 is also going to be bound to 6. All right, and then we end up having, let me just draw this nicely. Yeah, so you see how there are many different ways that you could put these two compounds together. Okay. There are totally other possibilities. I'm not going to go over all of them for time, but yeah, anyone have any questions on this page? Okay, so now we have some alkene reactions and we want to go in and identify any possible stereoisomers. Okay, so first of all, we're doing H2PDC onto this guy. Okay, so essentially remember I'm going and I am reducing this to, I'm going to be reducing this to the single bonds. Do I form any chiral centers here?
Yeah.
No.
I heard yes and no at the same time. So you do actually, because you see here that you have 1 carbon here, you have 1, 2 here, and then you have 1, 2, 3. Okay, so this would be 1 stereoisomer, and then the other one would just be the same thing, but with it being dashed. And I totally forget, what is this reaction? Is it syn or anti or both?
Then
Yep, this is syn only. All right, HBr, what is the stereochem of that? Syn, anti, or both?
Both.
Both syn and anti. Doesn't really matter too much in this particular case because when you go and then you add in your bromine, you're going to end up with essentially the same products, except now you have a bromine there on that tertiary carbon. So here you just form 2 stereoisomers because you only form 1 new chiral center. All right. Next one. So PHCOOOH. What does that do again?
The epoxide.
Yep, it forms an epoxide, and that is syn only. An anti-epoxide would be very unstable. But yeah, you would have an epoxide either looking like this or an epoxide that looks like this. Okay. Notice that here I'm like working out these problems without drawing the mechanism. You guys should be able, hopefully by now, to work out these problems without having to draw the whole mechanism, especially for BH3THF, because that is a very ugly mechanism. Oh yeah, so these are the only 2 you get. BH3THF, is that syn, anti, or both?
then
Yep, syn only. Cool. So yeah, because of that, even though you form 2 new chiral centers, you only get 2 stereoisomers, right? Because you can only have it such that your BH3 and your THF add syn. So here's one. And here's the other. Cool. NBS and water, syn, anti, or both?
Anti?
Anti, right? Because remember, the whole premise of that mechanism is that you undergo that bromonium ion and you have to break it by attacking from the opposite side. Okay, so for this, what you're gonna get is that your bromine, so it ends up on one side and then your alcohol on the other. Remember, because it's water, you're adding in an alcohol. And same thing over here. Cool. Sulfuric acid and ethanol. This is an interesting one. What does that do?
Both syn and anti.
Yep, so this is both syn and anti. But one thing that's very notable about this particular reaction is the fact that, you know, it's water, and so it's the same thing as water and sulfuric acid. Except instead of making an alcohol, you're going to be making an ether because you're using ethanol here. Okay, so essentially what you end up getting is both of these, or here you're only going to be getting one stereoisomer. And that's going to be where you are adding in your OET rather than your alcohol. Okay, now let's say I wanted to go in and make this, maybe I added an extra carbon here. Then in that case, I would have two different stereoisomers. I would have this one, and I would have this one. So don't get tricked out by that. Cool. Ozonolysis, you know that's going to break your carbon-carbon bond over here. So it's not syn or anti, you just end up getting these two products. Okay, and then lastly, you have OSO4. Remember OSO4, that's your dihydroxylation. So what your dihydroxylation does is that you're going to add in alcohols on either side. So like this. And remember that this reaction is syn only. Cool. So remember that if you have a reaction that's syn and anti, it undergoes a carbocation. Okay. So I guess just to kind of quickly recap. So syn adds at the same time. Anti, the only anti reactions, are the bromonium ion ones. And then syn and anti, those undergo a carbocation intermediate. So that's how you can see what it does based off of the mechanism. Cool. Any questions on this?
Sorry, for the H2SO4 one, do we only need to draw one product?
Yeah, you only draw one product, but I added a methyl group here just to make it asymmetric, so you could draw two. But for the actual answer to that would only be just one.
So if we drew a second one, would it be marked incorrect?
Avoid it if you can.
Gotcha. Okay, thanks.
Cool. All right, number 5. So this one is dealing with the ever so famous Falzone Sneaky and his little stereochem games that he likes to play with you guys. Now notice that for this one right here, we're ending up with alcohols on either side. Okay, and then we end up seeing that we have so these two vicinal alcohols right here, we know that the reaction for this would have to be OSO4. And that would apply for both of these reactions. Now, the only difference though is that, where did you add across, right? So here you see that, it's supposed to be a syn only reaction. And we have here, it looks like it added syn, right? You have the two wedges there. And this backbone looks like it came from like some sort of a trans double bond. Okay, so because of that, it'll be, what we have here is that you would have to reduce this alkyne to a trans double bond. It'll be NaNH3 at negative 78 degrees Celsius. Likewise, for the other one, you would have had to, let me just rotate this here. In order for it to add syn, it would needed to add like this. That molecule you see there is just rotated. So because of that, you see that your backbone over here was cis. Okay, so that means that you needed to use H2 Lindlar's catalyst first. All right, and then for the next one, you see that you have this OH and Br right next to each other. Okay, and then you know that the reaction that gives you OH and Br right next to each other is going to be NBS and water. But you know that reaction adds anti only. Okay, so the fact that it looks syn here means that you would have had to rotate once again. And that means that in that case, if you would have had to rotate, that means it would have added like this. Okay, so because of that, that means that once again, you would have had to use the cis. So H2 Lindlar's. Okay, and then for the last reaction, still the same reaction. And you're using Na and NH3 for this one. Cool. And then this one, last of exam 2, it says to draw the major product of the following reaction in the box below. Okay, so it says here that stereochem is not required, but you're also allowing for one carbocation rearrangement to occur. Well, here you see you have a 7-membered ring and a 4-membered ring, both pretty unstable. However, if you went and drew out a mechanism for this, you will end up seeing that you end up with this. So you have a positive charge here. I'm actually going to number just to make life easier. 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice that I didn't number all the carbons. I just numbered, oh, dang it, it froze again. Yeah, so like that. Yeah, so I didn't number everything, just the one that I find relevant, but you could do it however you want. Okay, but then afterwards, you're gonna go ahead and do your little rearrangement here. Boo, boo. So that ends up looking a little like this initially. But your cation will move from carbon 1 over to carbon 2. All right. So then that means that we end up getting this with the carbocation in this position. When water attacks, it'll come in and then attack over here. And of course, you have to deprotonate after. I'm not going to show that deprotonation step, but you're going to end up getting a product that looks like this. All right. Well, any questions on this page? Okay, so now let's go and then move on to our exam 3 material. And we start off with a question about aromaticity. So label the following molecules as aromatic, anti-aromatic, or not aromatic. Cool. Remember that your criteria for aromaticity are going to be that you need to have an odd number of pi electron pairs, or a Huckel number, whatever you want to call it. You're planar. You're fully cyclic pi system. And your ring has all sp2 atoms. Okay, so looking at the first one over here, you see that you only have one pair of pi electrons. The dication might throw you off, but it's still planar, so it's going to be anti-aromatic. Sorry, it's going to be aromatic, not anti. Okay, next one. So you see that you have, these two pairs of pi electrons here. However, you have this atom right here. Okay, this atom is actually sp3 because it has two hydrogens. So because of that, this is not aromatic. All right, next one. So let's assume planarity here. I know Falzone always pretty much assumes planarity. Okay, if we assume planarity, you see that you have a total of 1, 2, 3, 4. So you have 4 pairs of pi electrons, which is even. That makes it anti-aromatic. And then remember that over here, boron has an empty p orbital, so it's almost like a carbocation. Okay, so then that means that boron is sp2. Otherwise, you have 1, 2, 3 pairs of pi electrons, so that makes that aromatic. Cool. So make sure you guys are aware of your criteria for aromaticity. Okay, right now for aromaticity, this and like maybe those other like cool problems or like the extent of like what you should need to know for this. All right, 2, complete the following reactions. So you see that we're going to have heat, and we only know one reaction that only uses heat, and that's going to be your Diels-Alder. Okay, and the way that that works is that we are going to, it helps to go and then draw your retro Diels-Alder arrows. Maybe it'll help if you number as well. And if you go ahead and then do that, this one is 10 up here, you're going to end up seeing that you have this with carbons 1, 2, 3, 4, 5, and then this over here. Six, 7, 8, 9, 10. Cool. Next one. So you see that we're starting off with only C4H6, and we are adding bromines on our 1 and 4 position. So 1, 2, 3, 4. Okay, so because it's 1, 4, looks like we should have had a conjugated diene. Again, molecular formula C4H6, which corresponds potentially to 1,3-butadiene. And then in order to get to your final product with this, all you would have to use is, again, Br2. And you're doing the 1,4 product that gives you the more substituted double bond. So it's going to be heat. Okay. Notice that here, this double bond is more substituted. Let me just highlight. And then this double bond is less substituted. And here looks like you just had the 1,2 product. Okay, so you would pretty much have the same thing. But instead of having heat, you would have had it at some low temperature. So I'll do maybe 0 degrees Celsius or -78. Cool. As long as it's something that's very clearly cold. And then you see for this last one over here that you start off with, a 4-carbon chain with 2 bromides at the end. And then here's this original 4-carbon chain, but you're adding in a total of 4 carbons, 2 on each side. Okay, so this is going to be your acetylide chemistry, right? And I'm actually gonna maybe draw it like a little outside the box, but remember, in order to do this, you would need, so acetylene, particularly 2 equivalents. And then in order to form your acetylide ion, you have to use NaNH2 and NH3. And you would end up with this acetylide ion. Cool. And
Just a quick note, when you guys are doing the BR2 with thermokinetic control, it'd be good to just include 1 equivalence, just to like make sure that they understand.
yep. If there's one thing I've never been good at, it's like it's been remembering the 1 equivalent for some reason. So don't make the same mistake as me. Do it. Definitely, that would probably, if I took an exam today, that would probably be the thing I get points off on. Cool. Any questions on this? Great. Give you guys like 10 seconds. I'll take like 10 seconds to breathe real quick.
Sorry to
Mhm.
bother your breathing, but could you
Fine.
just walk through the first part again, the Diels-Alder reaction?
So, that Diels-Alder is supposed to form a 6-membered ring, right? So your cyclohexene. So that's this one right here. Now, if I were to go and then, remember, I have to go and then pretty much form my bonds over here. These sigma bonds are going to be the ones that were made, so they break. Right, and then initially, I'm going to draw this kind of ugly, but what you're going to see. So you would have this thing, right? That like 5-membered ring. But then if you're going to draw it nicely, like a little, like that cyclopentadiene, then it would end up looking like this. Does that make sense? Cool.
Yes, thank you.
All right. Synthesis and then some NMR. All right, so it says to provide a synthesis for each of the following molecules using the indicated starting material. Okay, so one thing to note, we start off with 4 carbons and we end up with 8 carbons. All right, so at some point we have to add 4 carbons in here. Well, notice that we had a way to add 4 carbons earlier, and that was through our thermodynamic BR2 addition followed by acetylide. So I'm going to start off by doing BR2 and heat, 1 equivalent, so I don't forget this time. So I would end up with this dibromide. And then afterwards, this would probably be the step where I'd want to go and then add in my 4 extra carbons. So I could do that by taking acetylide. Remember, that's always a nice source of 2 carbons, as usual. 2 equivalents, NaNH2, NH3. Form your acetylide ion. And you're going to end up with this intermediate. And then notice that here you have an aldehyde at the end, and an alcohol in the middle. There's actually one reaction that you can do that can give us all that just in one, or like technically 2 steps. And that would be 9-BBN. So step 1, 9-BBN, THF. I would denote excess. And then second step, your workup. Cool. So that's your first synthesis. And then your second one, I do want to turn you guys' attention to this little pattern that you should be familiar with. 1, 2, 3, 4, 5, 6. So here you have a 1,6 dicarbonyl. Okay. 1,6 dicarbonyls are very indicative of are usually indicative of Diels-Alder ozonolysis. Okay. And that's, remember, because if you have it 1,6, then that means that you had a 6-membered ring. Okay, so then you would have had there's a reason why I'm not accounting for that 3rd carbonyl. Okay, so then you would end up having that. Okay, now you had that 1,3-butadiene that you ended up forming here, and then you had this conjugated aldehyde that you would have used for your dienophile. Remember, that would have just looked like this. And that would have been what you had to do for this synthesis. Cool. Then you have this last 3rd synthesis on this page. All right, so one little piece of advice: you guys do not know any reactions that work on aromatic rings yet. Okay, none of the reactions you know will do anything to an aromatic ring. So basically, for your purposes right now, this has no functional groups on it. There's only one way that we can add a functional group onto this, and that would be by doing NBS and UV light to give you your benzylic bromination. Okay, notice that here at some point we have to add in our 2 extra carbons. And we can go ahead and do that by adding acetylide, as we usually have. Okay, and then now we have the carbons that we want. We just want to try and get this carbonyl over here. Okay, so notice that the carbonyl is in the Markovnikov position. So the only reaction you know that would do that would be water and sulfuric acid. If you use 9-BBN, you'll get the aldehyde, not the ketone. Okay, any questions on either of these, any of these 3 syntheses? Cool. And don't forget that syntheses, like, these are not like the hard right answers. Okay, technically there could be some other ways that you could do them, especially in Orgo 2. So if you happen to get stuck on a synthesis and you come up with like a long way that's technically correct, that gets you to the right answer, but you can't find out like a quicker way than just do the longer way, you'll lose some points, but it's better to get partial credit than none. All right, number 4. So, for NMR, and then that's the end of the exam 3 material. All right, yeah, not too far from the end. We'll probably be going a little bit later, but you guys don't have to stay for that. It'll be recorded. So for problem 4, provide an organic structure that is consistent with the following spectra. Okay, so before I do anything, C11H12O4. I want to find how many degrees of unsaturation I have. How many degrees of unsaturation do I have?
6.
6 degrees of unsaturation, that's right. Okay, and then here I have my carbon NMR spectrum. Particularly, you see that I have these two peaks right here. If you look on the back of your exam, you see that that will particularly correspond to maybe a carboxylic acid or ester region. Just put a little question mark just in case you're questioning it. But remember, anything past 160 is likely indicative of some sort of a carbonyl. Cool. Now, if you know me, you know I love making my little chart. Chemical shift, number of hydrogens, multiplicity, possibilities. Okay, so I'm gonna go in and I'm gonna start off by like labeling or writing down each of these peaks. So I have 8.1. That's going to integrate to 2, and it's a doublet. I have one at 7.3. 2 doublet. I have one at 4.3. It's going to integrate to 2, and it's a quartet. I have one that's at 2.3. Integrates to 3 and is a singlet. And lastly, I have another one that's at about 1.3. That's 3, and that's also going to be a triplet. Okay, cool. So right off the bat, do you guys notice any particular region or pattern that we can potentially say that we're going to have?
Doublet of doublets.
Well, we have 2 doublets, yes. What do you think those are going to represent?
A benzene.
Benzene with what kind of substitution pattern?
Para.
Para?
Para, yeah. So notice that your peaks integrate to 4, meaning that you have 4 protons in the benzene ring, and they're going to be para substituted. The way you know that it's para is because they're very nice and like evenly split. Okay. Now for these peaks that you have over here, remember we have 2 peaks in that carboxylic acid or ester region. Cool. If we had to choose between carboxylic acid and ester, what do you think it might be and why?
Ester, because there's no hydrogen in the 11 to 12 ppm region.
Yep, that's right. So it can't be a carboxylic acid because you don't have that broad singlet at 11 to 12-ish. So we'll likely have 2 esters here. Now, remember that esters tend to be a little tricky because you have to find like the proper orientation for an ester. Okay, so we have 2 of them. Now, do you have any peaks here that could potentially, that look like they can potentially be part of one side of an ester?
The 2.3 singlet could be next to the oxygen that's double bonded.
Yep, so this is likely going to be a CH3 like this. Very good. So that takes care of this side over here. And then what about the other one? Or the other 2 peaks that you have there?
The 2 hydrogens at 4.3 would be next to the single bonded oxygen. And
Yep.
then that would be next to the methyl group.
Right, so yes, I'll just draw this down here. So we would see that we would have a CH2 right next to a CH3, right? And then you see that the splitting patterns will add up. Okay. Now you know that these have to be across 2 different esters because we only have, like these peaks to work with. So I could say that this will potentially be next to like part of the other ester that you have here. All right, cool. So looks like we have all of our degrees of unsaturation. We have everything we need. We just got to go and then stitch everything together. So we know it's para substituted. And then we could say on one side, we're going to have the ester with the ethyl group. And then on the other side, we're going to have the ester, but where the oxygen is facing the benzene ring. Cool. And then that adds up to the structure that we have for this compound. Cool. Any questions on this?
How do you know the O is next to benzene again?
I mean, just by process of elimination. I mean, you can also tell by like this peak over here that it's so far downfield in the carbon NMR that it would likely correspond to this carbon over here. Okay, but like also just notice that there's no other potential place that it can go and be para substituted like that.
Okay.
Okay, cool. Now work on this spectrum. Sam, what do you want to, since it's 157, what do you want to do? Should we just like keep going until we finish and then people who want to go and go? Or
Yeah, if that works with you, we can just keep running this and then I'll send out the recording to anyone who couldn't watch the last few minutes of it.
yeah, sure, sounds good. All right, yeah, so this is going to be the last question for exam 3, and then I have the final exam portion, which you're welcome to stay for, or you're welcome to watch in the recording when it's out. All right, so again, we have a molecular formula of C11H15Cl. How many degrees of unsaturation do I have here?
4.
4, very good. All right, so I'm looking at my IR. My IR doesn't really give me anything too useful, okay? Remember, if you had a carbonyls would probably show up at around like this region-ish, or like this around here. And there's also no numbers that are labeled. So if there's no numbers that are labeled, usually it's not going to be that important to us. Okay, mass spec doesn't look like it's telling us anything too useful. And then carbon NMR. So let's see, carbon NMR, we don't have anything in the carbonyl region, which totally makes sense because we have no oxygens. And we do have a bunch of CH2 here. Here's the CH2 here, so that can potentially work for us. We'll come back to that in a bit. All right, I'm gonna go and then, as usual, make my little handy dandy chart. Okay, so I have these little peaks at 7.3 and 7. I'll call it 7.3 and 7.1. That has 2, and that's going to be a doublet. Okay. So we have one at 4.5. That integrates to 2. Oh, so everything's a 2 except for the last one. 2, and that's going to be a singlet. We have a peak at 2.5. Okay, 2.5, we said that that's a triplet. Then 2, what do we have? Pentet, sextet, okay. Let's call that 1.6 and then 1.2. And then we have a peak, not a triplet, at 1.0. Okay, so let's go and then put everything that we have together. So you guys know the drill, okay? What do you think we have that will give us something right off the bat?
Parabenzene.
Yep, parabenzene once again. Nice clean splitting in their aromatic region. Integrates to 4 in total. Very concerned looking benzene ring as usual. Cool, so I have that. Let's see what I potentially have. So I have, my usual 3, that's a triplet. right? If I have a 3 that's a triplet, what does that usually mean for me?
A CH3 bonded to a CH2.
CH3 next to CH2, very good. Okay, and then moving along, I see that all my other peaks are going to integrate to 2. So it's probably going to be my several CH2s that I have there. So everything will need to be a CH2 besides that CH3. So if I have a CH2 there with another CH2 neighboring, so then first of all, this will probably be that orange CH2, and that will be probably CH3, CH2, and next to CH2. Okay, that way it'll be a sextet. I don't really think putting a CH there is a good idea because of the fact that you don't have any peaks that integrate to 1. Could potentially work in like some other problem, but here it doesn't really check out. Okay, and then the next one, so we have a CH2. Let's say if that CH2 is next to another CH2, it would be a pentet. So it would likely be the yellow one. CH2, CH2. I am completely writing into the spectrum. That's fine. Okay. You have one here, and the CH2 that you have over here, it has to be that next CH2 has to be the triplet. It can't be the singlet because then it wouldn't be next to any other peak. So it'll be like this. And then likewise, that gray one would just be a CH2 only next to another CH2. Cool. And then that S right there, it's really, really upfield or really, really downfield, notice. So that's likely actually, if you look at your chart, it'll probably be the CH2 that's next to the chlorine. And then on the other side, it'll probably just be the benzene ring. All right, so now we have all of our fragments. We can go and then put everything together. So on one end, we would have the CH2Cl like this. Then on the other end, we would have our 1, 2, 3, like this. Cool, and then this is our structure. Cool, totally crammed my work there towards the bottom, but any questions on this, on any of the last 2 NMRs? Okay, now we're going to go into our final section of the problem set and our final exam section of like this problem set as well. Yeah, so here you see that we have NaOET and ethanol, right? And we also do have a secondary leaving group, which is our OTOS. Okay, so yep, notice that it's secondary, and sodium ethoxide is actually a good base. So regardless of whether or not you had heat in here, you would do the same mechanism. The question is, which mechanism will you be doing? E2, very good. So yeah, so it's going to be an elimination mechanism, right? Remember, it's a good base. If it were primary, it would probably do a substitution, just like acetylide. But because it's secondary, you are going to have to resort to doing an elimination. That's just because it's a good base. Okay, it has a pK above 10. So I want to go in and find my anti-periplanar proton to eliminate. So am I going to form my Zaitsev or my Hoffman product?
Hoffman.
Hoffman, very good. Because over here, I don't have an anti-periplanar hydrogen. Here I do. So I go and I take my electrons, eliminate here, pluck off that OTOS, and end up with this cyclohexene. All right, next up, we have this tert butoxide, right? Very, very strong base, very bulky base. And we have a primary bromide, okay? Now, because tert butoxide is actually so bulky, its possibility of doing a substitution is very, very, very low, okay? It's not like methoxide or ethoxide. So this will also be an E2. Again, this is where things get tricky because you have to know like roughly like how good everything is. And I know many of you have asked me to like draw like make a list of like good nucleophiles and good bases. Even if I make a list like that, it's not really going to be too helpful. It's going to be entirely situational based off of your substrate. Your pKHR and your acid base chapter is your best friend.
For this one, Juan, I was imagining it more deprotonating your alcohol and then doing an SN2.
Deprotonating your alcohol and then doing an SN2. Interesting. I feel like I've seen examples with alcohols, what's it called? Like with alcohols being on there, but then they'll still like want to do the elimination. But I guess, actually, no, yeah, you're right. Yeah, that could probably work. Yeah, I'm probably thinking about something else. Yeah, so you have an acidic proton here on your alcohol. Go and then eliminate. No, so I was thinking about E1CB. That's why. Yeah, because I know that the enolate, or like when you form the enolate, like for like the dehydration or whatever, you do an E1CB. Right. So then you go and then deprotonate. Okay, and then you end up forming. I'll do this over here on the side. Your tert butanol. Okay, and then you see that from here, you're going to do an intermolecular reaction, which is actually very favorable. 1, 2, 3, 4, 5. You're going to form a 5-membered ring. So we're going to form a THF ring with a methyl group on it, and that will be an SN2. So yeah, again, be careful with your bases. That's why knowing your acid base chapter is very, very important. All right, next one is a very classic example. Okay, I know it's kind of blocked, or not really blocked by my arrow, but it's kind of like right there. Sulfuric acid and heat with a tertiary alcohol. What kind of reaction does that remind us of?
Elimination.
Okay, what kind?
E1.
This is going to be your E1. Okay, so where you go and then remember you would go and form that good leaving group. Okay, just by protonating your sulfuric acid. That leaves on its own because sulfuric acid's conjugate base is a very weak base. Then you would just go and then eliminate here. All right, cool. And then this next one, tert butoxide and fluorine. What kind of reaction do we expect here?
E2.
Why E2?
It would be E1CB, right?
E1CB. Why that?
Fluorine is a bad leaving group.
Yep, that's exactly right. So if you see a fluorine, unless you have another good leaving group on there, that's pretty much going to be an E1CB, right? I know Falzone has some examples where he'll have a fluorine and then an iodine and ask you which reaction occurs. Eliminate the iodine before the fluorine, please, because that's going to be the better leaving group. And then hence that will be an E2 instead. But here we don't have that. So remember, we want to form our stable carbanion, right? And then afterwards, like once we form our stable carbanion, we would go and eliminate. So we'd end up with this. Cool. And that will be your E1CB. All right. Sam, what were you trying to go for in this last one?
What was that?
Were you just trying to go for like no reaction in this last one? Or
I was doing SN1.
SN1? Do you mean to have like a different leaving group on there?
Yeah.
Okay, yeah. So let's make that OTAS, because why not? Okay. Yeah, so OTAS, you know that's a good leaving group, so you want to go and kick that off. So you form this carbocation, right? Afterwards, you would go and then add in your nitrile. And you end up getting this final product. Pop quiz, how many stereoisomers do you form here?
1.
Why only one?
No chiral center.
Yep, you don't form a chiral center here. Cool. All right, any questions on this whole page?
Can you talk about why the secondary OTAS is important in the first one?
So the reason why it's important there is because if it were primary, a smaller base like sodium ethoxide could potentially do an SN2 instead. So like I've seen examples of like this. Right? You've seen something very similar with acetylide, right? Where acetylide, if it's primary, if your leaving group is primary, it'll do a substitution. But if it's secondary, it'll do an elimination. That makes sense?
Yeah, thank you.
Yeah, no problem. Okay. 2 pages left, guys. All right. For this one, we want to complete the following reactions that indicate stereochemistry. So first, we're going to be using PBr3. So in the past, we've seen that PBr3 will do an SN2 to go and then convert your stereocenter into, or convert your alcohol into a good leaving group. Are we going to be doing an SN2 here?
Yes.
How come?
Doesn't it flip the configuration?
So ideally, that's what you would want. But notice your alcohol. Your alcohol is tertiary, and eventually you're going to go and then end up with this as your leaving group. Okay, sorry, like this. So when your leaving group is like that, doesn't matter what kind of reaction you're gonna do an SN1. So you get that carbocation, and then the bromine can add in from either side, hence giving you this product or this product. Okay, so remember you only invert the stereocenter if you do an SN2, which in this case you can't. What about the tosyl chloride? How many stereoisomers will you end up with here?
One.
Why only one? So do we do any substitution at all in the tosyl chloride reaction?
No.
No, we don't. So we would end up with just one stereoisomer. So this would be the only thing we would end up with. Okay, because remember how like when I did the OTAS mechanism, I would always label it like, oh, like SN2, SN2, no SN2 here. Okay, there would just be no substitution at all there.
Juan, for the first one, are you sure that you get two products? Because I seem to recall that you always just get the inverted product.
That's if you do an SN2.
Okay.
Yeah.
You know when you're doing an SN2 and when you're not.
So remember, whenever you form a stable carbocation, you end up doing an SN1. Okay. Remember that SN2 doesn't want to occur if your substrate is too hindered.
So if it was on a secondary carbon, then it would invert only.
Yeah, then it would do an SN2. So like if you had, I'll draw like a separate example here. So in that case, that would be good enough to do an SN2. So in that here, you would only end up forming this one. Okay, but in this case, you would undergo the SN1 here. Okay. Now for this one, so Poco 3, pyridine. Do you remember what that reaction does?
Elimination. So E1 here.
This one would actually just be an E2, okay? Because like the base that you use is like not that bad. So the thing is here in this case, you would probably end up with two major products. Either this one or this one. Okay, those are two different states of products that you can get here. Your product that has this guy up here, like this, it can also form, but it'll probably form in a lot less actually, yeah, no, it'll form in a lot less quantities because it's less substituted than the other two. All right, and then thionyl chloride, very similar reaction to your PBr3. You will still undergo that SN1. So unless it's secondary, then you will have to. Yeah, unless it's secondary, or if it's secondary, then you would usually just invert. But here you're once again doing an SN1, so you get a mixture of both. So like this. So of all your alcohol activations, if you were trying to end up with like a leaving group and only one product, you would probably want to do this one if you had a tertiary alcohol for that reason. Cool. Any questions on this?
Is POCO3 always E2?
POCO3, yeah, always E2.
For the Poco example, are you saying that the top molecule we got is the major product, or both of those make up the major product?
Both of them are, because you have the same substitution for both.
Okay, so would you say that that's a 50-50 split? Or I guess not 50-50, but like in same amounts, yeah.
Like relatively, I guess relatively close. I wouldn't say I don't know how much one would form over the other, but they would be relatively close.
Okay.
All right, last page. So draw the products of the following reactions and determining which one has a larger KEQ. Okay, so we have hydrochloric acid. So that will go ahead and get protonated here. Oop. And then to get this product, you'd go and then break this off. Okay, doing so will end up with 1, 2, 3, 4, 5. So then this will be one of your products, and then the other product, I'm not going to draw the mechanism, but it's essentially the same thing, but with a ring that has one extra carbon. All right, which of these reactions do you think will have the larger KEQ?
The second one.
How come?
It's unstable ring, wants to be more stable.
Right, so we would expect that the equilibrium would lie more towards the products. for this one, whereas over here, it'll actually lie more towards the starting material, right? We don't really like having, oh, what's it called? Yeah, we don't really like having this, we don't like having a large ring, and we also don't like breaking stable rings. So that's why the bottom reaction would have a larger KEQ. And then this one would have a smaller KEQ. Cool. Any questions on this? Okay, 2 problems left. And then, yeah, so here you see it asks us to complete the following reaction and determine how many possible isomers, including stereoisomers, can be formed as final products. Okay, so first of all, when we go in and do this elimination, what 2 different products might you expect that we form here?
One with the double bond on the end and one with the double bond in the middle.
So the one with the double bond on the ends might not be one of your major products, or I guess like you form one more major, one more minor, I guess, but you would actually want to form, so this one would be your major. Okay, and then this other one, right, would be your minor because it's still the Hofmann product, but you still have another anti-periplanar proton that you can eliminate. Cool, so you have these 2, and then finally you could just go and then use this reagent, which makes your epoxide, and you're going to end up forming either this product and these. So for each of those, for each one, you would end up getting a total of 4 stereo. For each one, you get a total of 2 stereoisomers for a total of, actually, no, you would actually only end up getting 3 because this guy right here is meso. Okay, so because this one's meso, that means that those last 2 that I drew are actually the same. So you end up getting a total of 3 stereoisomers. Cool. Any questions on that? Okay, and last but not least, our very last problem for this problem set. So it says to draw all the possible monobrominated products of the following reaction. Okay, I'm gonna give myself a little more space. I'm gonna copy paste this onto the next page. All right, so here, the fact that we're using NBS, the peroxide, sometimes he includes it, no big deal. It still does the same thing. You want to go and then brominate your allylic positions. Okay, so that means that you would end up forming your radicals there. And then, of course, with allylic bromination, you know that there are possible resonance structures here too. So you want to go ahead and then try drawing those resonance structures. So you get one like this. You get one like this. And then you end up getting one like this. So of all these, Are there any identical resonance structures that would result in the same compound?
Blue.
Yep, the top ones are identical. All right, so when I go and then brominate those, I end up with one here. One here. One here. Here. And here. All right, so then these would be your 5 products. Cool. Any questions on this? All right, well, that's the problem set. No, it was a rather long one, but of course, if you didn't get anything, we'll be posting the recording later on so you can maybe like catch up on something. Yeah, so hopefully this helps give you guys a little more confidence with solving problems. Of course, make sure that you guys continue solving them your own. And yeah, good luck with your studying.
Thank you so much.
Can
Thanks,
I ask a quick question?